Lastly, we come to the case of rocket propulsion, because it's possible to understand how rockets are propelled using the concepts of perfectly inelastic collision. Okay? In fact, it's like a perfectly inelastic collision, except in reverse. Remember, in perfectly inelastic, you first have two objects, they collide, they join together, they get entangled and move as one. In the case of our rocket, we have two objects which are already joined together. That's our basic rocket structure and the fuel that it's carrying. And after not exactly a collision, but after some time, some of this fuel is reduced by being burnt out. Okay? And so the objects separate out, if you like, and then it's looking at it in reverse. We first had them joined together, but after a process, they are separated, right? So we will use the concepts of perfectly inelastic collision to understand this system. Here's a rocket, it's being thrust upwards, okay? So our system consists of the rocket, its basic structure which stays together, plus the ejected fuel. And when that fuel is burned and the gases from the combustion are basically ejected backwards, that provides a forward thrust in order to have linear momentum conserved, okay? So the thrust depends on how fast the exhaust gases get accelerated in the opposite direction, okay? So here's my system. Let's try to understand it. At the start, we have the mass of the rocket, this uppercase M, plus the mass of some fuel, which is going to change with time, yeah? So the momentum is this total mass times the total velocity of both systems as they're traveling together, yeah? Okay, that's my initial momentum. And after some time, some of the fuel has been burned up, may or may not be all of it. Over here, we show that all of it has been burned up, and so its mass is gone, that little delta n. This is just the mass of the rocket, and it has accelerated, so its velocity has increased by an amount, delta v. Yeah? So that change in velocity, remember, that's the acceleration. The change in velocity is proportional to the velocity of the exhaust gases and how fast the mass of the total system is reduced. So this is the initial mass divided by the final mass. Final could be at any point in time that you're looking at it. And this is the natural logarithm of this ratio, okay? So Mi is the initial mass of the rocket plus the fuel. Mf is the final mass of the rocket plus any remaining fuel, depending on what time you're looking at it. So the speed of the rocket is going to be proportional to the exhaust speed here, okay? That's an important thing. And typically, this is of the order of several kilometers per second. So 10 to the power 3 meters per second. Now, if you want to figure out the thrust, which is the force that drives the rocket, the force is given by mass times acceleration, yeah? So mass of the rocket times its acceleration. Acceleration is nothing but the change in velocity with time, okay? And we knew something about velocity that we just saw. It's related to how fast you burn the fuel, and it's related to the exhaust velocity. So in fact, it turns out to be this. We will not derive it, but you should know this equation, that the thrust equals the modulus, or the absolute value of the exhaust velocity. This could be negative, its direction doesn't matter here, and the rate of burning the fuel, okay? So let's do a very simple problem on this. At liftoff, the engines of Saturn V rocket consumed 13,000 kgs per second. Kg per second. This is telling you how fast the fuel burned. And exhausted the combustion, 13,000 kgs per second of fuel, and exhausted the combustion products at 2,900 meters per second. So that's my exhaust velocity. What is the total upward force or thrust provided by the engines? So you really just have to use this equation. You need to use this number is 2,900. This one is 13,000. You need to multiply those two together. And what you get is 3.77 times 10 to the power 7 newtons. So you don't have to memorize these equations. You can bring them on a sheet of paper with you in the final exam. You'll be given a certain size of index card that you can use, okay? let's look at the three important factors for a rocket. You want it to accelerate as fast as possible. Therefore, you want to increase its exhaust velocity as much as possible. You want to burn the fuel as fast as possible so that this number goes up. And you also want the rocket to have as small a mass as possible, since the thrust is mass times acceleration. So the smaller the mass, the greater the acceleration. Yeah? Okay. We'll stop here. And after this, in the PowerPoint, you will see that there are a few more example problems which you are welcome to go over by yourself. But we have now covered all the curriculum material for this chapter. So we're going to stop here.